It's a pleasure to welcome Semeon Artamonov from UC Berkeley. And it's a pleasure to hear about Poisson geometry of non-commutative cluster algebras. I will have questions in mind.
So,
please.
Thank you very much, Professor Berkeley, and it's a great pleasure to speak at this wonderful seminar. So, my talk will be largely based on our joint paper with Nick Ovenhouse and Misha Shapiro, which is titled Noncommutative Networks on a Cylinder, and also some prior work during my PhD thesis under the supervision of Professor Retak at Rutgers, and our long-standing collaboration with Professor Rubtsov as well. So, as a warm-up, let me start by saying a few words on the usual cluster algebras. And I, of course, apologize to those of you who know a lot about cluster algebras, and there are some experts in the audience, I know. But let me still kind of describe the idea of the cluster algebras before proceeding to their non-commutative generalization. So the cluster algebras were first introduced in a paper by S.Fomin and A.Zelevinsky around the year 2002. So here's the reference, and they introduced the cluster algebras as a very special type of the commutative algebras with kind of distinguished presentation. And this was done in an attempt to in the work to describe canonical basis of the universal enveloping algebra of the Borel subalgebra of a simple Lie algebra. So in short, the cluster algebra is a commutative algebra. Algebra with a very special type of presentation. With a very special type of a presentation. And kind of the generators of this presentation are grouped into overlapping subsets called clusters. Generators are grouped into overlapping subsets. And that's what's called clusters, and give a name to the cluster algebra. And there are no relations between generators in the single clusters. Generators in one cluster, one cluster. So there is a copy of the polynomial ring sitting inside your cluster algebra associated to every cluster, and kind of defining relations. Yes. Relations which are called mutations. Well, they are associated to pairs of clusters. Are associated to, well, some, not all pairs, just some pairs. Of clusters clusters, and also have a very special form. So I'm not going into the technical details of the definition of the cluster algebra because I have only finite amount of time. But let me kind of give a simplest example, actually the prototypical example of a cluster algebra. So, and by the way, in the chat I posted a link. Sorry. I post a link to the chat to the Blackboard, so you can scroll it independently. So you don't have to be confined to a single screen I'm currently writing on. Okay, so let me, instead of giving the precise definition of a cluster algebra, let me kind of describe the prototypical example. So, and the prototypical example of a cluster algebra is the coordinate ring, of SL2. So one can think of it as an algebraic variety, right? Which has the coordinate ring, which is generated by 4 variables, say x11, x12, x21, and x22, which describe the corresponding components of a matrix, right? Subject to a single relation. And that's of course that the determinant equals to 1, which I will write in the following form, that x11, x22 equals to 1 plus x12, x21. And let me call this relation star. Okay, so one can think of it as a cluster algebra with 2 charts. Can think. Two charts. So the first chart will be defined by the subset of the generators, let's say x11, x12, and x21. x12 and x21. There are no relations between them, so there is a copy of the polynomial ring sits in A, right? And similarly, there is another cluster chart. Let's take x22, x12, x21. Well, kind of what we can immediately note that informally one can think of relation star as the following expression. So we can think that somehow x11 is a Laurent polynomial in the variables of the second chart, x2, x21, x22 is Laurent polynomial in the variables of second chart. And of course, same is true, with positive integer coefficients. And of course, the same is true for x22. Okay, so the axioms of the cluster algebra, they essentially formalize these requirements, and there are a few different versions of the definition of a cluster algebra, but all of them boil to one and the same thing. So essentially, axioms of the cluster algebra are created to formalize the above properties. And somehow encode the relations of your commutative algebra. And code kind of cluster charts into, well, by oriented colored graphs, variables, well, generators of cluster chart by edges, or depending on your description, by vertices of the graph. And finally, the mutations, which are the relations in your overall commutative algebra by certain transformations of graphs. So in other words, it provides some combinatorial structure behind this commutative ring. And it turns out that a lot of fairly complicated commutative rings, which have rather difficult presentation in terms of generators and relations, do in fact come from the cluster algebra. So the combinatorial structure behind the cluster algebra represent the interest on its own, and that's essentially where kind of the situation got out of hand, and the study of the combinatorial structure behind the cluster algebras turned into, we know today, as a major topic, where a lot of people kind of investigate the combinatorics of the cluster algebras. Okay, so in my talk, I will be interested in a particular example of the cluster algebras, the so-called geometric cluster algebras, and kind of the important property of this cluster algebras, as well as most of the relevant cluster algebras, is that they can be equipped with a Poisson bracket. So let me kind of give the reference of the original paper, which introduced Poisson brackets on cluster algebras. So the first kind of the first appearance of that was in the paper by Gechtman, Shapiro, and Weinstein around the year 2003. So that's the, and what they did, they showed that kind of most of the relevant examples of the cluster algebra come with a natural Poisson bracket, which can be determined using the same combinatorial data as the original cluster algebra. Most cluster algebras can be equipped with a Poisson bracket. And moreover, this Poisson bracket will preserve the cluster charts. preserving the cluster charts. So another way you can think of it as, so the cluster charts are essentially a polynomial subalgebras inside your cluster algebra. So you can equip all of them with a Poisson bracket, and this Poisson bracket will be compatible with the mutations. Well, in other words, it extends into entire cluster algebra given in terms of generators and relations. Okay, so let me kind of move on to the next paragraph, paragraph 1, geometric cluster algebras. Cluster algebras. And of course, I encourage questions at any moment of my talk. So if you want to ask a question, please feel free to interrupt me at any moment. Okay, so the geometric cluster algebras are a special type, special example of the cluster algebras, which are kind of which were first introduced by Postnikov in his study of Grassmannians. Here's the original paper, and that was the cluster algebras associated to some networks in a disk. Then it was enhanced by introducing the Poisson brackets. And finally, kind of this disks, networks in a disk were also extended to networks in a cylinder or in the annulus, depending how you would like to think about the cylinder. And that was due to Gechtman, Shapiro, and Weinstein around year 2012. So kind of the geometric cluster algebras are defined. Okay, so let's talk about the networks on a cylinder. So networks on a cylinder. There, and this somehow let's say the simplest case without loops, etc. So there are some generalization of that. And kind of the cluster chart in this case is determined by the following graph. So let's say we have a cylinder. Say we have a cylinder, and we will think, we will look at the directed network with, let's say, n inputs. And n outputs. Inputs and n outputs. Okay, so then you draw the bipartite directed graph with the following property that at every step the number of horizontal arrows is the same, and you're allowed to have trivalent vertices. So the white vertex will have 2 outgoing edges and 1 ingoing, and the black vertex would be the opposite of that. And the only non-horizontal kind of edges are allowed are kind of vertical, which come between the neighboring strands, like this. And because we're in a cylinder, we can also have something like this. We can have the edge, which kind of winds around the cylinder and returns here. So that will be the graph which describes particular chart. The variables of the chart will be assigned to edges of this graph. So let's say we have x1, x2, x2, x3, x4, x5, etc. And the mutations essentially will be associated to a rectangle like here. So this was cluster chart. Cluster chart. And mutation. For the mutation, you take a part of this graph which looks as a rectangle. We have four relations. So, and there will be integrable systems on this phase space. Okay, so let me kind of briefly.
So the distinction you're making is that the lax matrix satisfies the R matrix Poisson bracket, and the Goldman bracket is not on that space, but somehow on the space of monodromies associated with that.
Exactly. Yes. Okay, so let me explain. Let me explain kind of the agenda here. So let's say we have a part of the graph like this. So what we will do, we will think of it as a ribbon graph. And what we will do next is we reverse the orientation of a ribbon graph at every black vertex. Now, topologically, this would correspond to essentially flipping the ribbon each time we move from a white vertex to a black vertex. So if we start with a graph like this, flipping here. So if we have a piece like this, then we will get a surface, which is called conjugate surface, associated to this ribbon graph, where essentially we connected everything by ribbons, and we flipped the ribbon each time we move from white to black vertex. Okay, and now if you look at loops, if you look at loop here, let's say that we take this loop, right? Then kind of we had our variables A, B. We had our variables A, B, C, D, and to the loop B, C, D, and to the loop we will associate kind of the product of them. So we will think of them as GL1 connections, and in this case that will be monodromy around this loop will be essentially A, B, C, and D inverse because we walk it in the opposite direction. Okay, so now this corresponds to some closed loop in our network, and kind of what you will do is if you compute the brackets between these two loops, between the two different loops, you will get precisely the Goldman bracket.
I have a question actually.
Yes.
So if you identify the ends of this cylinder, is this the Poisson bracket that you would get from the Goncharov-Kenyon integrable system?
Yes, that's correct.
You have dimers on a torus.
Yes, and actually, this picture is precisely about the dimers on a torus. Actually, since this came up, let me put kind of another reference here, and kind of very closely related systems were considered by Goncharov and Kenyon in this paper. But then they considered kind of, instead of looking at the networks on a cylinder with the same number of inputs and outputs, they looked at an arbitrary kind of triangulation of a surface and the graphs associated to triangulations. But what I'm talking is the particular case of the Goncharov-Kenyon, of course. So now if you draw the loops, right, on this conjugate surface, which consisted of these flipped ribbons, then these loops, for example, M1 and M2, they will have intersections. And with these intersections, you can associate the Goldman bracket. So GL1 kind of Goldman bracket, Goldman bracket on GL1 connections on conjugate surface. surface. So if you have two paths, M1 and M2, then the bracket between them will be the sum over all intersection points. One intersect with M2, epsilon of P, 1, M2. So where epsilon of P is the sign of the intersection, so which is +1 when we have, so those are two directed loops. When the we move from the positive direction of M1 to M2 in the counterclockwise, and -1 in the opposite. 2 point P 2.
Sorry, just a question. But this surface, this conjugate surface that you define, is it orientable?
Yes, that's so yeah. Sorry, I didn't say it explicitly.
So but what makes it orientable? Just the fact that it's.
So the moment I said that we think of our graph as a ribbon graph implies that we think of it as an oriented surface with the orientation induced by our cylinder on which the original graph is drawn.
Okay.
And once we flip the orientation at all the black vertices, we get a new orientable surface, right? Which is this graph consisted of twisted ribbons.
Mm-hmm.
And precisely because we need orientation, of course, to define the Goldman bracket.
Okay.
Okay, so now the main question. Main question can we generalize this construction? This construction beyond GL1. And kind of the spoiler is that in fact one can solve this problem in all GLN, and for that matter SLN simultaneously. By noncommutative geometry. And that's precisely the content of our paper. So what one can do is one can introduce the so-called quasi-Poisson, double quasi-Poisson bracket directly in terms of open arcs on the conjugate surface. And this quasi-Poisson bracket, double quasi-Poisson bracket, it will induce the usual quasi-Poisson brackets on the representation spaces of the of our fundamental groupoid. And
sorry, Semeon, could
yes?
you give a definition of quasi-Poisson bracket?
Yes, that's kind of that's what I'm about to do. So let's move on to that. So double. Okay, so that will be paragraph 2. Double Quasi-Poisson brackets on open arcs. Okay, so what is the usual Poisson bracket? It's a skew-symmetric bivector, right, which satisfies the Jacobi identity. So we somehow want to generalize the idea of a bivector to non-commutative algebra. So we want to have, so first, we want to have some form of the Leibniz identity. Okay, so kind of definition. So let A be an associative, not necessarily commutative, not necessarily commutative algebra. Let's say over C, the double derivation is a map, and that will be a map from A tensor A to itself to A tensor A, satisfying two Leibniz identities. So first, if we take kind of the bracket with the product BC in the second place, then what we will get is we will get B tensor 1 multiplied by the bracket between A and C, and A bracket B multiplied by 1 tensor C. And also we will have a Leibniz identity with respect to the first argument. And that will be 1 tensor A multiplied by the bracket BC plus the bracket between A and C multiplied by B tensor 1. So kind of why you need this is because if you kind of require, if you try to generalize the idea of the Poisson bracket naively to the case of non-commutative algebra and kind of ask what about kind of the the object, which would be a skew-symmetric biderivation in the usual sense, which satisfies the Jacobi identity, then there is a kind of remarkable theorem that as long as you have at least two elements in your algebra which don't commute, then this definition is just a multiple of the commutator. So in order to have a meaningful definition of a Poisson bracket on a non-commutative algebra, you have to replace the codomain. You have to replace the codomain with A tensor A and use two different Leibniz identities. So A tensor A has two independent structure of an A bimodule, the outer A bimodule and the inner A bimodule. And you have to kind of say that your double bracket satisfies the Leibniz identity, two different Leibniz identity. For the first argument, it will satisfy the Leibniz identity as an inner A bimodule, and for the kind of induced by the inner A bimodule structure on A tensor A, and with respect to the second argument, it will satisfy the Leibniz identity induced by the outer bimodule structure on A tensor A. So this idea originates from the so-called double geometry, which unfortunately I don't have much time to talk about. So let me just give you two main references which appeared about the same time. So one of them is the paper by Crowley, Boevi, Itchenkoff, and Ginsburg, where they explained why you need essentially A tensor A as a codomain of a bivector field. And
may I just ask the question by
yes.
you? Isn't this just a, it's like an abstraction and formalization of the usual notion of, Poisson bracket for matrices that was like this St. Petersburg notation?
Perfect. That's that's absolutely correct. Because the double Poisson bracket, not quasi bracket, the double Poisson bracket induces usual Poisson brackets on matrix representations of your algebra. So that's absolutely correct, and that's of course the idea.
But so what makes it quasi? Where is the quasi?
And what makes it the quasi is the right-hand side of the Jacobi identity.
Oh, okay.
So now kind of another definition of the
but actually the St. Petersburg bracket is already a quasi in the sense that it's you simultaneously take tensor products and Poisson brackets. So you end up on the right-hand side with something in the tensor product.
That's right, but it induces kind of what's
yeah, there's an underlying Poisson bracket, but the thing that is written down is actually a map to the tensor product. It's actually.
Because I think Semeon is saying that what is going to define does not satisfy the Jacobi identity, or some weaker version, right?
Yes,
no,
that's
but
right.
what I mean is that the St. Petersburg bracket is a genuine Poisson bracket.
Yes.
But it's formulated. It's formulated as a bracket on the tensor product spaces, mapping tensor product to tensor products. But underneath it is an ordinary Poisson bracket that satisfies Jacobi identity.
Well, it's in the case of the double Poisson bracket. So there are kind of okay. So let me put this definition. Definition A. So double Poisson bracket, double Poisson bracket is a skew-symmetric, well, special form of the skew-symmetric. I won't go into that. Metric biderivation satisfying double Jacobi identity. So if you take A, B, and then bracket C, and you take left, then you cyclically permute and put tau 1, 2, 3 to that B, C, A plus tau 1, 3, 2, composed with C, A, B. And by L, I mean that it's applied to the left argument of the result of the BC here. Then you will get 0. And there is another thing, which is a quasi-Poisson bracket. So definition B, double quasi-Poisson bracket. Poisson bracket is essentially where you have this quasi-Jacobi identity, but on the right on the right, you don't have 0. Instead, you have a fixed trivector. Fixed trivector, which vanishes when you close loops. When you take traces of closed loops, well, matrices associated to closed loops.
Is that sort of a co-boundary condition?
Yes.
So you can think of this as cohomology.
Loops. You can think of it as a cohomology, and in fact, you have a very nice formula for this fixed trivector. So kind of there's a great story about polyvector fields on non-commutative algebras, and this right-hand side of the double Quasi-Poisson bracket can be interpreted as the co-boundary condition. That's absolutely correct. So kind of oh, I'm doing terribly with the time. So now let me just give you a formula. So one can define them on the loops on a surface with a boundary, and this is due to the paper by Masayo and Turaev. And in fact, one can enhance the results of the Masayo and Turaev. One can enhance their results by considering open loops. And I'm not kind of, that's what I did in my thesis. So one can generalize their construction to the case of open loops. And the formula is as nice as it can potentially get. So if you have let's say that you have some surface, then you put the marked points on the boundary, and because your surface is oriented, the orientation of a surface induces the total order of edges adjacent to the marked points. So in this case, if you have P1, right? So that's your surface, that's the boundary. Then if you look at the morphisms, you will have F3, you will have incoming F1, you will have outgoing F2, ingoing F2, and finally, the last one is outgoing F4. And there is a total ordering on those. There's a total ordering given by the orientation of a surface. So kind of, and what you do if you have this surface, and let's say you have a number of morphisms x1, x2, xn. So the contribution to the bivector, so let's say this is PA. So the contribution to the bivector is essentially 1/2 sum of I less than j of the following thing: xi d by dxi, xj d by dxj, minus xj d by dxi, xi. Okay, so here's j, I, j, 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 I. So this defines the Quasi-Poisson bracket.
But the x's here are non-commuting?
The x's here are non-commuting. And these derivatives are non-commutative vector fields. So d by d fi of fj, let's say. So suppose it's freely generated by fi and fj, then this derivative will be one identity on the source of fi, tensor with identity on the target of fi, if I equals to j and 0 otherwise. So this d by dxi, this is non-commutative vector field. Non-commutative vector field. And there is a category of non-commutative vector fields. You can compose them. So you can compose them, and that's what's precisely going here. So like with the usual polyvector field, you can multiply and you can get a bivector field. And that's a non-commutative bivector, which is actually a map from a tensor A to a cube. Then you can take the trace of this bivector, and that will be your double bracket. Okay, so since I'm running out of time, let me kind of bring the main theorem. So theorem, and that's joined in our paper with Nick and Misha Shapiro. So the above Quasi-Poisson bracket, well, double Quasi-Poisson bracket, double Quasi-Poisson bracket, bracket on boundary measurement matrix, on boundary measurement matrix,
which you didn't define, but
which I didn't define. I'm sorry about that. So satisfy our matrix relation, and that's basically kind of if you take the bracket. If you take the bracket between b of lambda and b of mu, the double bracket. So now this will be a matrix. This will be a matrix whose elements are elements of whose elements are elements of a tensor A. So then what you will get is, okay, so let me, so the formula will be correct.
Sorry, what is non-commutative here? Where is the non-commutativity? You mean that the edge variables are non-commutative variables?
Sorry.
Yeah, sorry.
So this double bracket actually can be written via the usual trigonometric R matrix, B, let's say BL of lambda tensor BR of mu, and BL is essentially the matrix B multiplied by the identity on the right. So it's an element of the tensor square minus BL of lambda tensor BR of mu multiplied by R of lambda mu.
The square
you transpose, you switch the two tensor components.
The square cross
because those are elements in a tensor A.
I think so, somehow Semeon, can you hear us? Hello?
Matrices.
Oh, I think he hit the mute button.
Elements in a tensor A. And And kind of, if you have this relation, you will get a non-commutative integral system. You get a bunch of trace integrals, which will Poisson commute with each other. And this will happen in, this will automatically induce integral systems. Well, I mean, this will automatically induce commuting Hamilton flows on all representation spaces. So that's kind of that's the main idea. So kind of the work of Gehman, Shapiro, and Weinstein can be generalized to the non-commutative geometry. Okay, so let me stop here because I'm over time already, and let me just answer
Guillermo, can you do something to let
yes,
Semeon, can you hear us?
Oh, do you hear me?
We hear you, Semeon, but
we hear you, but you don't hear us.
I just sent him a message saying that.
Oh, sorry. So sorry. Yes, my disconnect.
Oh, right.
Can you hear us?
Yes. Sorry, sir.
Okay. Yeah, we were trying to ask you something for the last 5 minutes, but you didn't hear us.
Sorry, I did press the mute button on my headset. It's so sorry about that.
Okay. So the conclusion is that you have these commuting invariants which are formed somehow, I don't know, out of trace variants or something under this R matrix Poisson bracket.
Yes.
And so does this give rise to new integrable systems?
So that's a good question. So that definitely gives rise to commuting Hamilton flows. Now, the question which we didn't address in the paper is whether the number of the commuting Hamilton flows is enough. So because that involves the calculation about the independence of this Hamilton flows on the representation spaces, etc.
Yeah.
But the expectation. The expectation, of course, is that there are enough of them in all GLN simultaneously.
Well, of course, the standard R matrix theory implies more than just, I mean, this type of Poisson bracket, in the standard result, it implies not just the existence of a maximal set of commuting Hamiltonians, but it also implies a kind of integral form for the flow. I mean, based on a sort of Riemann-Hilbert factorization. I guess that's asking too much at this point.
Oh, no. We actually this is the part we have partially addressed. So at least on the formal level, we can describe the flow. But now, kind of what was kind of easy in the commutative world is that you had the underlying Lie group behind the Lie algebra.
Yes.
And this is what completely breaks in the non-commutative setup because you can pretty much generalize everything kind of related to the Lie algebra, right? But now if you're trying to exponentiate that, you immediately end up in the completion of your non-commutative algebra in the formal series in the completion, and proving statements there is a little bit difficult. So kind of some of the statements from refactorization flows and so on, they are generalized, and that's what we written kind of in the last chapter of the paper. But yeah, so of course like the usual. So we have all the statements concerning the Lux metrics and the flows there.
I have a couple of questions. So what is the non-commutativity here? What is non-commutative?
So kind of the elements of our this axis are arcs on the surface. And not I mean we can whenever they are composable, the composition is non-commutative.
No, but in the theorem, what are the entries of B?
Yes, sorry, I didn't explain that, but the entries of B is the following. So suppose we have n inputs and n outputs. So now kind of the ij entry of B will kind of have the sum of all oriented paths from I to j.
Okay.
So B is the boundary measurement matrix?
Yes, B is the boundary measurement matrix.
But
So that's
numerical matrix. The entries of B, are they operators or numbers?
Entries of B are formal linear combinations of arcs.
In any case, they're elements of an associative non-commutative algebra.
Yes.
Okay.
So
now our matrix. Let's talk about our matrix. What is it?
R matrix is the standard trigonometric R matrix, like literally the same one. Just an element of the ground field. Nothing fancy there.
And what do you mean by this fancy tensor product with the square?
So there is essentially there is a tensor because so here the tensor product is reserved for the tensor product in A, right? So we have A tensor A, and the box tensor product is the tensor product of matrices.
Oh, I see. Okay, just as ordinary
Product.
But A here is the algebra of paths.
Well, A here is actually kind of the ring with many objects. That's k pi 1 with your sigma with endpoints. I mean, it's not an algebra really. It's a group. It's a linear. It's a linear category, a small linear category generated by the groupoid.
But so just to match it with standard notion of boundary measurement map, right? So you have edges with weights, and then to each path they associate the product of the weights, and then you sum over all paths.
Yes.
So what you're saying is that you should have a homomorphism from pi 1 to some ring.
No, so the whole point is you do it literally in terms of pi 1.
Pi 1, okay.
Yeah. So
no, okay, yeah, but to get that, if you have a homomorphism from pi 1 to a ring, then you get the standard measurement map with values in that ring.
Yes, and it automatically induces the quasi-Poisson bracket on the space of representations, and if you take traces, then it will be usual Poisson brackets on kind of on the characters.
So could I ask maybe? So the first question is this rational nature of the A matrix. Is it related to the fact that we are working on the torus or on the cylinder, and you expect the elliptic A matrix to be
that's
torus, and then what happens if you have two boundary components and something of high genus in between?
That's a perfect question, and the story get much more complicated. So let me first answer why this is a trigonometric R matrix, and that's of course related to the fact that our original network were on the cylinder. So let me. Yeah. So you can think. So let's say you have a regional matrix on the cylinder. Each time you wind through the back, you add a spectral parameter. And then you close this cylinder, but you kind of remember the starting points. Those are indices of your boundary measurement matrix. So now you look at the paths on a closed torus, which however start and terminate only at one of these endpoints. you get the honest boundary measurement in terms of these paths. And you get the double bracket on this paths, and they will satisfy this this Bellevin R matrix relation, the brackets between them. Now, if you try, instead of cylinder, if you try to look at the networks on some kind of more complicated surface, so let's say you have one component here, and then you will have a hole there, right?
Yeah.
Then you will have another hole there. Then from the technical viewpoint, what happens is now you're allowed to go over that handle.
Yeah.
Of course, the resulting boundary measurement matrix, you can still get the brackets. That's the important thing. Kind of from this construction, you still get the brackets, but they will no longer satisfy the Bellevin-Drinfeld R matrix. The boundary measurement matrix will no longer satisfy the Bellevin-Drinfeld R matrix relation with a trigonometric R matrix.
Yeah,
in fact, kind of in short, we don't know what to replace it with, because somehow you need to put essentially if you do it instead of a cylinder, if you do it on a general surface, then kind of the powers of the spectral parameter, they were essentially tracing the fundamental group of a cylinder. So now this R matrix should live in somehow the tensor square of the fundamental group of that surface, and this is kind of this is of course I mean an open question to write this down, but we have the left hand side, so we have the boundary measurement matrix, we have the Quasi-Poisson bracket. It's kind of, we just don't, I mean it's just kind of really non-trivial way to, I mean, really non-trivial question what you need to replace the R matrix with in this case. I expect
but
that
can you not do it on a torus and have an elliptic R matrix?
Maybe.
So there is some question that kind of I expect let me say it this way. I expect it to be more complicated than that, but I might be wrong, because we don't kind of there's a difference between the fundamental group of a closed torus and, for example, of a torus with a boundary. And I really will be surprised if somehow one can get away with taking the Z cross Z instead of honest free group with two generators in this construction. So on a cylinder, that was easy, right? Because the fundamental group was Z. And I would expect that when we have really a torus here, that we can just introduce the elliptic R matrix, but we'd rather have to generalize the whole idea of the R matrix for the K pi 1 of this surface. But I mean, because I don't have the definitive answer for that question. It's just.
So maybe because also in terms of time, maybe let's thank the speaker. Maybe if you have more question, we can continue. So thanks, Semeon.